Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline, you'll need somewhere to deploy it, so check out Linode. With private networking, shared block storage, node balancers, and a 40 gigabit network, all controlled by a brand new API, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today to get a $20 credit and launch a new server in under a minute. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And join the discussion at dataengineeringpodcast.com/chat. Your host is Tobias Macy, and today I'm interviewing Ryan Blue about Iceberg, a Netflix project to implement a high-performance table format for batch workloads. So Ryan, could you start by introducing yourself?
Yeah, sure. I'm Ryan Blue. I work for Netflix on the data platform team.
And do you remember how you first got involved in the area of data management?
Yeah, mostly through distributed systems. So I've been working in the distributed system space for, I guess, most of my career, starting with like private projects for the company I was working for at that time. Eventually moved into the Hadoop space and then got hooked up with a job at Cloudera. From Cloudera, I was working on like file formats and data storage APIs, and eventually met up with the guys at Netflix and decided to move over here. So
yeah, I saw that you were working on Avro and I believe Parquet as well when you were at Cloudera.
Yeah, exactly. I was actually the one-man file formats team there for a while. So yeah, I got to know Avro and Parquet pretty well, which transferred over here to Netflix nicely. It was a good move. And then once at Netflix, I started working on like Spark, and basically my experience on file formats and the low level like data storage stuff was how I shouldn't say stuck. Let me think. My experience at Cloudera with like data formats and stuff was what landed me our projects for working with S3 tables. So like our batch pattern write projects and our S3 committers and stuff like that. So that's how I got into the format and table space.
Yeah, I had a great conversation a while back with Doug Cutting and Julian Ledem talking about Avro and Parquet and some of the finer points of data serialization and when you want to use which one. So that was a fun conversation.
Oh, yeah. Yeah, those are two of the best people to talk to on it, too.
And so that brings us to the work you're doing now with Iceberg. So can you give a brief explanation about what Iceberg is at the high level and what the original motivation was for creating it?
So Iceberg is a table format, and that's not something that in the Hadoop space we think about very often because we only have one, and it's sort of this ubiquitous table layout that we don't even think of. It's so pervasive. So Hive lays out data files in a directory structure, and then we basically go look at that directory structure and see, this partition is this directory, and then all the files in that directory are in my table. Iceberg takes that concept, basically how you know which files are in your table, what files make up the data set itself. And instead of tracking that the way Hive does it in a directory structure and with listing partition directories, Iceberg tracks files in a very different way. Well, I guess it's not very different, but just a different way. So really, Iceberg, the original concept was about how do we improve on keeping track of what data is in a table. Then the project grew from there just a little bit because we quickly realized that if we're going to fix this one aspect of how tables work, then we may as well fix some of the other sort of, what would you call them? The other challenges that we were hitting with those tables. So things like schema evolution is really tricky and not well defined across file formats and in different situations, as well as like how partitioning is done, so like the hidden versus explicit partitions. So we decided to expand the scope somewhat from there, but it's really about how do I track what data is in a table and the metadata for a table.
And given that Iceberg is primarily a metadata representation of the underlying files within these various directory hierarchies or partition hierarchies, how much of it is responsible for how the data is actually read through the query engine that's executing? Or is it merely just as a means of being able to locate those files for the query engine to then be able to retrieve and process them?
So the main purpose is to keep track of the list of files in the table for passing off to a query engine. So Iceberg core itself is really just that metadata component. Now, because we also get into fixing things like schema evolution, and basically how do I take a file that was written, a long time ago and read it using the table's current schema, we have to get involved somewhat in the engines themselves. So Iceberg provides, or Iceberg core provides, Iceberg core itself provides some helper functions for doing those projections and basically saying, hey, here's my Iceberg schema. I want to get records out of this file. But it also uses the approach of like the Parquet file format, in that you can bring your own object model and you implement some API and you can get records reconstructed in whatever your in-memory model is.
And so for the files that are contained within these hierarchies, do they have to be homogeneous in that they're all of the same format and all of the same schema within a given table structure or within a given directory structure? Or is there room for heterogeneity in the serialization formats or in the state of the schema across individual files? And then within those files themselves, is it sort of one record per file, or is each file a collection of multiple records and the sort of aggregation of those records is just determined by whatever process wrote them out to disk?
Yeah, it's the latter. The files in a table are whatever aggregation was necessary or optimal for whatever wrote it out to disk. So that reflects like your runtime query engine. Often users are trying to meet some SLA for getting this data done and out to the next level in a pipeline or next consumer. And we want to be able to use whatever parallelism is necessary to meet that deadline. So grouping records into files is all up to the query engine. And I should say at this point that I know you asked about schema as well. And that was a big question. What was the other one?
Whether the files within a directory structure can be heterogeneous or if they all need to be homogeneous.
Yeah. So back to the point right after your question. We want the processing engines to be able to do whatever's necessary there. Where Iceberg differs slightly is that it uses a model that gives you snapshot isolation between writers. So it makes it easier to have something that needs to write out a lot of smaller files to meet some SLA. And then we can have another process go in and compact those files to be optimal for the table offline. And that way we get sort of the best of both worlds. You can write data files for an availability deadline, but then you can also come back and compact them and write them another time for long-term storage. And that kind of dovetails into your question on, do these all have to be the same file format? Can they be different formats? The answer there is they can be different formats. Every file is, the format of every file is tracked individually. So we can have Avro files or ORC files or Parquet files all in the same table, and they should behave exactly the same way. That allows us to do things like have a streaming data system, streaming data into a record-oriented format, because it makes sense for the memory requirements of that streaming system. And then again, we can come back and either merge and shift those into a different format, or simply merge the files in the same format. We can clean up those artifacts of the initial processing later.
And it's also worth mentioning and pointing out that you were very careful to refer to Iceberg core during your earlier response, and also worth pointing out the fact that you have written a fairly extensive specification for the table format itself. So I'm wondering if you can talk about your reasoning for committing all of that to a document and what the current state of that specification is and its relation to the open source software project that bears the same name.
Oh, yeah. So one of the problems that we identified with the way most tables work in the, for lack of a better name, de facto or Hive table format, is that there's no specification for it. So this is kind of like when someone thinks they can write a CSV file by just adding commas to print statements, right? You're going to work 99% of the time, but there are edge cases that you're not going to think about ahead of time, right? So what we wanted was to eliminate the huge number of just slightly different implementations of the table format, or at least prevent that from happening for Iceberg. So our motivation here is that because we've taken the time to come up with what we think is a good and fairly future-proof design. Shouldn't call it future-proof. That's crazy. um, so our motivation here is that because we've taken the time to design this for a lot of the characteristics that we think we're going to need in the next few years, we want to push this to share it with other companies and hopefully make this a standard, just like the Hive table standard is today. And as long as we're doing that, we want to prevent sort of the accidental fragmentation that we've seen in the Hive table standard, where Presto and Hive have slightly different implementations, and things like how do I track nulls and partitions, or when do I escape partition values? Like all of those things aren't written down anywhere. So it's really easy to come up with a 90% solution, but it has all these slight little bugs. And this is something that I've personally had to deal with here at Netflix because, we have things that have our own implementation or parse partition keys and things like that. And then inevitably you realize that you weren't escaping partition values and you didn't handle nulls correctly. And all of these things, just eventually come around to bite you. So we wanted to be really careful about that.
So it sounds like it would be fair to say that the Hive table format is the markdown of the big data world.
Yeah, I think that might be a pretty apt analogy. Everyone has a slightly different flavor of it. I think it works pretty well because there is a standard implementation you can come back to. A reference implementation you can come back to and point and say, hey, Hive does it this way. And Hive was usually the first to, figure out these problems existed. So that at least it has going for it.
And the software implementation that you are using as the reference for your day-to-day work in the project is, as I mentioned before, open source. And I'm wondering if that was the intent from day one, or if there was some effort necessary to clean up some of the code base to make it publicly consumable after the fact.
Absolutely, it was our intent to open source this project. So we knew that a lot of the challenges we were seeing are not specific to Netflix. In fact, I don't think any of these challenges are specific to Netflix. There are a couple of reasons why we had, I think, a greater motivation than most people to solve the challenges, and that's primarily our use of S3. But even if you take a look at those, S3 has more correctness issues if you're using the Hive table layout. There's still correctness issues with the Hive table layout in HDFS, and there are still scale challenges with the Hive table layout in HDFS. And those are our two main motivating factors, both of which are made worse by using S3, but they're by no means, just gone if you're using HDFS instead.
And on that note, how has the use of Iceberg simplified your work at Netflix for those batch workloads?
Well, we're still rolling it out, so I don't know if I'd say it's simplified any of my work yet. um, the main thing that it's going to do is it will replace a number of projects that we've been maintaining. And maybe projects is a not the right word. It replaces a number of workarounds that we have for working with S3. So we've given talks in the past at conferences and I think done blog posts about things like Semper, which is our consistent listing solution for S3, which is basically where we hijack file system calls and make sure that we check a consistent database for what we expect from those list calls, so that when we say, I want to read this partition, give me all the files in it, we know that we got all of the files instead of some of the files, because that's a correctness problem. So because Iceberg tracks all of the files in a table individually, we no longer have to list directories. So we no longer have consistent listing issues. And on that note, we no longer have the issues where we're listing too many directories. So things that we've done to solve both of those challenges in the past, like Semper for consistent listing and hacks in our S3 file system to make those listing calls faster, we no longer really need, because Iceberg is just not listing in S3, which is, we think, a better design for both S3 and HDFS based tables. So really, it's taking all of these things that we've done in the past and rethinking how we interact with the underlying data file system. So in the past, we've just tried to integrate with S3 at the file system level. How do we make our file system faster? How do we guarantee consistent listings? How do we avoid renames? Things like that. And what we've realized the problem is that we're using a table format that requires listing and renames and all of those things that are slow. So by using Iceberg, we no longer need those things.
And so how is the actual software implementation of Iceberg implemented and designed, and how has that architecture evolved since you first began working on it?
So Iceberg is at the core just a metadata layer for keeping track of snapshots of file listings in the table. It's evolved quite a bit in that it came from that high level idea of, let's track all the files in the table at time t equals 1, t equals 2, etc. We really had to do a lot of work to figure out, how are we going to make this feasible? We've had to think, how do we list these files and keep track of them? Then how do we make sure we're not writing too much on every, to keep track of metadata for every application level write and things like that. And it has grown significantly in scope as we realize that we need to do things like have an expression library so that you can pass an expression to Iceberg so we can filter the files that you need, as well as pass that down into the file formats so that we can take advantage of Parquet row group pruning and things like that.
And for the actual deployment and integration with somebody's query engine, what's involved in getting it installed and set up and configured to be able to use within somebody's existing workflow?
Good question. So right now, there's one main challenge, and that is how we keep track of the pointer to the top level metadata. So Iceberg manages metadata, well, I guess data files and metadata files in a Git-like tree structure. So you've got one metadata file at the top that keeps track of the valid snapshots of a table. Those valid snapshots point to manifest files that list the data files, and then those data files are stored somewhere as well. So you can think of it as a tree structure. And we guarantee atomic transactions on the table by simply writing a new version of this tree, just like you would with a new Git commit, and then pointing the current reference to the new version of the tree. the new root. So here at Netflix, we have a system called Metacat that we use as a federated Hive metastore. And we use Metacat for that pointing to the root metadata of a table. So that's a challenge if you're not here, because we need to figure out some way to keep track of which metadata file is current. So that's the first challenge. And for that, in the public space, we just committed a implementation that uses locking and a generic Hive metastore. So we're testing that out, and I think our Presto support is going to be based on that. So it'll use a regular Hive metastore and use that Hive metastore to do this pointer update from one version of table metadata to the next. We also have a version of this that uses just an HDFS path, either HDFS or local file system, I should say, because a file system with atomic rename can also be used to keep track of the metadata without, I'm trying to think of a good way to simply say that we need this atomic commit. So we also have an implementation that uses either the local file system or HDFS, or basically any file system with atomic rename, to also keep track of what the current metadata for a table is. So those two implementations are public, and we're testing those out and trying to integrate them with the public parts of the project. And I should mention, the only non-public part of the project is our own integration with Metacat. I think Metacat's public, so even that might be public soon anyway. So that's the first challenge, is how do we keep track of table metadata? So that's the challenge of how do we keep track of Iceberg tables? Then there's the challenge of, how do I deliver Iceberg to the query engine that I'm using? We're building Iceberg integration with Presto, Spark, read-only integration in Pig, and then client libraries in Python and Java. So Spark and Presto are really the two main ones that I think people will be using in the near future. Like I said, we just released the Hive support for using a Hive metastore to keep track of tables. And that was the only thing that our Presto implementation was waiting for. So we're going to be posting a pull request in the next week or two with integration with Presto that uses that Hive integration or Hive metastore to track your tables. Then in the project, there's also a module called Iceberg Runtime. And that's a shaded jar that contains everything that you need in order to get Iceberg working with Spark 2.3. There's version 0.2.0, which you can use with Spark 2.3, and 0.3.0, which you can use with Spark 2.3.2. So that should just, you drop it into your Spark class path, and then you can load Iceberg tables using the data frame API.
And do you have a migration path either implemented or planned for people who are moving from their existing Hive tables to using Iceberg within their query engines?
Yes, there is a pretty easy migration path. Our internal Spark version has all the table DDL and things like that implemented, and we're working on getting those things out into the public version of Spark, or the upstream Spark version. So we've basically built it out, tested it out here, and we're working on getting those features into upstream Spark through the new data source v2 API in Spark. So once that's out, or once our Presto support is out, it'll be very easy to create tables using just regular SQL DDL. So the migration path would be create an Iceberg table using normal create table DDL, and then insert into or create table as select from one table to another. So that's the easiest path. It's slightly harder if you don't want to copy your data. And there are only some situations where you can avoid copying your data. So if your tables are currently in CSV or JSON or formats that we don't really think of as database formats, I shouldn't say database formats, but high performance database formats. If your tables are in those formats, then you would need to forklift your code or your data and copy it in. there are some cases, if your data is already in Orc or Parquet or Avro, where you could just build your Iceberg metadata and point to all those existing files. Now, the only trick there is we're going to have some sort of mapping from the schemas in those files to an Iceberg schema. Iceberg schemas are different because we want the same schema implementation across all the different formats. So Orc, Avro, and Parquet. And we do schema evolution differently. We use field IDs to keep track of every data field in a schema. That way we can do adds and drops and renames that match the behavior of traditional SQL databases.
And in terms of the schema for the individual files on disk, how do you manage evolution of those schemas that is managed at the Iceberg table level and propagating that down to the actual files on disk?
So Iceberg has a pretty strict set of rules for schema evolution. It actually implements exactly what you can do in SQL DDL. So it aligns very nicely. But you can add columns, drop columns, rename, etc. To track those changes, or basically to track columns themselves, we use field IDs. So when we're writing data out to disk, we write the field IDs into the schemas of the files that we're writing. So Parquet and Avro, for example, we just embed the field IDs in their schemas so that when we read the file, we can do our resolution based on the field IDs and then project the correct columns. And we use field IDs so that we can get rid of some of the edge cases where in Avro, for example, if you delete a column and then re-add that a column with the same name, you'll get the old data. So we have to use something unique. So we just have a one-up counter that assigns a new ID for every column. That way, if you dropped column A, where the ID was 6, and you add column A, you get a new ID for that, say 7. And we consider those two unique columns in the data.
And in the process of mutating the schema at the table level, do you actually modify the underlying files themselves, or do you just modify what actually gets read out from those files when you issue a query to the Iceberg table for the query planning?
Good question. So using this ID system, we don't have to modify any of the underlying files. We can guarantee that schema evolution works exactly as you would expect it to without modifying the data itself. So like I said, when you drop a column, you really just say, hey, I'm never going to need ID 7 again, or something like that. When you add a column, you know that it's not going to conflict with any existing data because it uses a fresh ID. And like renames and things like that, because projection is always based on IDs, the name of a column always comes from the table's current schema. So whatever the table's current schema says that the name of that column is, the name of that column. So the names from the files themselves don't matter.
And so earlier you had mentioned that one of the provisions built into Iceberg is the ability to compact the underlying data files from maybe Avro or Parquet into new representations of that data. And so does that compaction rely on the currently defined schema such that if you do that drop and add back in of a column, if the column ID that was present when the file was first written isn't the same as what is there now, will that information be discarded during that compaction process?
So that actually depends on the engine that you're using to do that compaction process. You could choose the newer of the two schemas. So, say I have file A and file B. If they have the same schema, then I can just continue using that schema and compact them together. The only guarantee that we make is that the newer of two schemas can read the older schema. So all of our schema transitions make that guarantee. That way you know that the current table schema can read any data schema in the table. So if you wanted to preserve as much data as possible, you could use the newer of all of the schemas of the files that you're compacting. So the schema that's actually used kind of depends on what's doing the compaction. The simple compaction case where you just say, hey, Spark, go read this data and then write back out and overwrite what I just read, that would certainly use the table's current schema. So yeah, that would discard data like you were saying.
And in terms of the table definition for a heterogeneous combination of files within that directory structure, how do you handle the case where a given file doesn't contain all of the fields that are specified in a given table definition?
What we do is if you've added a new column, that column has to be optional because we realize that not all of the data files in the table may have that column. So any new column has to be optional, just like I think Avro schema evolution requires. And so when the read happens, optional fields that aren't present in a particular file are filled in with nulls. So that's a slight departure from the way other systems act, where you can set a default. In Iceberg schemas, the default is always null because we wanted to avoid the problem that you run into with Avro files, which is that you can't tell if a value was in the file or was the value of the default. So we always default to null. And at this time, what we're doing is allowing the query engine to use something like a coalesce to fill in values. I don't think it's the right place to put the default values at the file format level and possibly not even the table format level, although I think the table format could do that. I'm not really sure. But what we're trying to do is make sure that we have very clear and well-defined rules for schema evolution to avoid cases like that.
And one of the most pernicious and complicated problems in data modeling, and particularly when you're dealing with large volumes of data and distributed systems, is that of managing table partitions. So I'm wondering how Iceberg helps in that regard.
Oh, so Iceberg fixes one of my pet peeves with with tables, and that's that there is no relationship in a Hive table between partition columns and the data those partition columns are derived from. So that sounds, kind of abstract. So let me give you a concrete example. We partition a lot of tables here by day or day and hour. So the simpler case is just by day. So I'll go with that. Now, this is a really common use case, right? Partitioning your data as it comes in from a streaming system by day or by timestamp. The problem with the way we do this currently is that when we store the data, we have something that goes through and takes a timestamp field and says, okay, I know how to derive a day from this timestamp. So it builds a date, a date string, and then stores that date string in a date column. So now we have a timestamp column and a date column. When you go and read a table, you can use the date column to prune all the partitions that you don't need. But you have this problem where if someone doesn't know the physical structure of the table, that it's partitioned by that date, or they don't know that they need to care about the physical structure of the table, they don't add the date column because they see this timestamp column and they think, oh, well, I know which timestamps I need, and a database is smart enough to figure it out. So what we end up with is novice users or users that are used to maybe SQL in other database systems, more traditional, expensive databases. They don't know that they need a query on partition columns. So what they end up with is a query that takes forever because they didn't know to add a date filter. What we do in Iceberg is we keep track of the relationship between that timestamp column, what we're deriving this date column from, and the date column that we're storing things by. That way, when that user comes and issues a query with a timestamp range, we know how to bake that down into a predicate that matches just the partitions or just the files that they also need. So hiding those partitions from the user is really valuable on the query side. And it's also incredibly useful on the write side because the query engine can be written just once to know, oh, here's how I derive a date from this timestamp, instead of pushing that problem onto users when they're storing data in their tables, because it's not easy to know the date function relies on some time zone or might behave weirdly in different situations. What we really want is to remove that decision or that problem from users so they don't have to think about it.
Yeah, it's always great to have the computer do what they're best at of performing the same task repeatedly every time they get the same type of input rather than relying on humans to remember to do that because humans are terrible at doing that.
Oh, exactly. And there are more benefits to doing this as well. So our initial motivation for basically having these partition transforms instead of partition columns was to take the human error out of generating that partition data and take the human error out of using that partition data. Once we realized that there was this separation between like the logical columns and this physical representation, though, how we store it on disk, we realized that this allows us to change how it's stored on disk. So we can take a table that's partitioned by day and change it into a table that's partitioned by hour. And the queries don't have to change because the queries are all written in terms of the timestamp column and not this weird derived column that you have to include for no reason. So it's really nice that this same principle gets us to the point where we can actually fix tables. We can actually fix tables that have had data volume increase over time, or maybe instead of when a user is creating a proof of concept, right? We can take the table that they use for that proof of concept and fix the partitioning on it instead of saying, okay, your proof of concept works, but you're going to have to go plan for your data volume in a couple years before you can move this to production. So it really smooths out that pipeline for our user base where they can test something out in an unpartitioned table and then just go update the table settings, or at least that's where we're headed. I don't think we have anything exposed other than me going out and changing the partitioning of a table at this point by hand, but that's definitely where we're headed.
And as you mentioned before, your primary data lake implementation is running on top of S3, which is becoming increasingly popular to use S3 and other object stores instead of the previous generation that relied on HDFS and other distributed file systems that were run by the data platform team. So I'm wondering, what are some of the unique challenges that are posed by the fact that you are using S3 as the basis for your data lake?
So I think we actually touched on this a bit earlier, where S3 has two main difficulties for us. So the first one is correctness due to S3's consistency guarantees. So we need to make sure that when we list a directory, which is actually going out and saying, hey, what paths have this prefix, or what object keys have some prefix, that we get the correct output there. We also have a unique challenge with S3 because it's a remote store. So a lot of the operations take maybe an order of magnitude longer than they do if you're hitting a name node in a local HDFS cluster. So those two things, you still have those challenges in HDFS, where if you're listing too many directories, it's slow. And there are still times, because of how the Hive table layout works, there are still times when, even if you get consistent listings, your query results can be incorrect. So you still have all these problems, but they're more pronounced for S3 tables. So that's why we were more motivated to fix these.
And what are the benefits of using the S3 file store as the basis for your platform that outweigh those difficulties?
First of all, it's really nice not having to have a static HDFS cluster. A lot of companies have to deal with problems where they have to keep their HDFS cluster up and running all the time. They have to worry about, how do we back up this HDFS cluster, all of the data in our cluster and things like that. For us, because we have separate compute and storage, we view our clusters as just ephemeral compute resources. So we can lose a cluster, lose a name node, and we just bring up another one in a couple minutes. Well, it might take longer to get the nodes, but we can bring up a cluster very, very quickly. So what we found is that separating compute and storage is really important for us because we can move a whole lot faster and don't have to maintain a lot of infrastructure. S3 is also great for us because they take care of the durability problems. They take care of worrying about like erasure coding and things that the HDFS community is just now really grappling with. So those are just handled for us. But I would definitely say that the major thing is not having to worry about long-lived clusters and what do we do with this persistent data that's sticky on those clusters.
And in terms of the specification that you're defining for Iceberg, you have published it as a Google Doc that anybody can go and comment on and suggest edits. And from looking at it, there seems to be a healthy amount of activity and people involved in that process. So I'm curious what you have found to be some of the most challenging or contentious details of the specification to define, and some of the discussions that have arisen out of those.
So the way that Iceberg tracks field IDs is a departure from what's already there. And I think a lot of people thought, we've already got by name, field resolution, why change it? And we were going for really make this so that users never have to care about a problem. And if I go add a ID column to my table and I find out that there was one 3 years ago that got deleted and now I'm getting bad data, that's a problem where we're leaking to users. But we've had questions and had some good discussions on why are we going to this length to make sure that those problems are eliminated? Why not just take a step back and say, we'll use some existing schemas and get through this problem. We've definitely had discussions with people that think, why go this far? But again, we really think it's a guarantee. We don't want our users to ever have to think, hey, did we have a column with this name 3 years back that's going to, ruin our long-term queries?
What are some of the things that you have explicitly left out of the specification, and have there been any discussions or disagreements that arose out of those omissions?
So there are a couple things. One that comes to mind is how to manage the manifest files that store all of the data files in the table. That's purposely ambiguous. So a snapshot of a table, the table state at some point in time is the union of all the data files listed in one or more manifests. And that is purposely vague so that we have a lot of flexibility with how we manage those manifests, how we compact them, how we write them out to optimize either, quick writes or overall, metadata size or things like that. And that's one of the areas where we think there's going to be a lot of improvement. We didn't want to preclude a lot of the designs that we could go with in the future. So we get a few questions about that. There's also some confusion over the fact that we don't have explicit partitions. So in Iceberg, you do partition data, but the format really tracks partitions as a tuple of data values that are the same for all rows in a data file. So you can think of files having partitions instead of partitions having files in Iceberg. And there's a lot of confusion over the fact that a manifest file can store a whole bunch of data files in any partition and not just a single partition. Then, there are healthy discussions on why use Avro as our underlying manifest format and things like that. And I think that we're pretty flexible on the long-term decisions here. We really want to go forward with something that works and the community is going to rally behind in the long term.
And what are your long-term goals for the Iceberg specification?
We really want Iceberg to take off in open source projects with people using tables in the big data space. We think that this is a pretty significant step forward in terms of the guarantees that the tables can make in big data. So like I said earlier, there are just times, unavoidable times, if you're using Hive tables, when a query against that table might produce incorrect results. And that's really just the fact that it's storing table state partially in the file system, and you can't have a transaction in HDFS or S3 that makes a whole bunch of files show up all at once. So there's just no way to have, unless you lock and make sure no one's reading the table until you're done writing and you confirm that all those files have shown up in listings. There's just no way to have consistency and therefore correctness. We think that having correctness solved, having schema evolution solved, having partition predicates and pruning solved, and some of these steps forward that Iceberg is delivering, we think that that's going to be pretty attractive to other companies and not just us. And we really hope that this becomes a community standard that is a successful open source project that we can all use and benefit from.
And do you think that the reference implementation that you're using today is going to continue to be used and maintained and evolved? Or do you think that once the specification has been sort of ratified and confirmed by a community consensus, that there will be other implementations that will eventually take its place?
I don't know when we would stop maintaining the current one. After all, we're building it into Presto. We're building it into Presto. We're building it into Spark. We've got a pig library. So, we're really using that one implementation in a lot of places. I think that's going to probably make the center of gravity in the Java world the reference implementation. That said, if there's a better one out there, then that's great. I hope that we really do standardize on a table format that can have multiple correct implementations. I still think that there is going to be one probably in the C++ world as well, and we're implementing something in Java. So sorry, of course we're implementing something in Java, and we're implementing one in Python as well. So there are definitely going to be multiple implementations of the table spec. And I just don't see a reason why the current one in the JVM space would be
superseded.
I mean, superseded if we stop maintaining it, certainly, but we're definitely all in on maintaining this.
And do you have any sort of timeline in mind or any criteria to determine when the specification itself can be deemed complete and brought to a community vote or through some sort of confirmation process to say this is the complete version of this specification at this point in time, so that there can be a stable reference point to work from if there are any revisions in the future?
Yeah, so I think that's going to require a couple of things. First of all, we want to get it to the point where there aren't things that we know we should probably change about it. And at this point, there are a couple things that we're thinking, yeah, we might want to change those. So, and I should mention that the Java reference implementation will have backward compatibility. I've worked in file formats for a long time, so I understand the forward and backward compatibility concerns, and we'll make that transition super smooth if it needs to be done. But there are some, completely compatible changes that we think we want to do, as well as at least one incompatible change that I think we're going to need. We would want the format to be stable for at least some period of time. And the other blocker for us to declare a stable format is really, once a community has formed around this. I think that the discussion on the doc has gone really well, and I'm very excited to see great people with good questions talking on that doc. Once we have that community of people and that are involved in the project, that care about the project, it's really going to that group of people and saying, hey, do we think that this is a finished specification that we can stamp a 1.0 on? Right now, I don't think that we've filled out that community of people that care and that would take part in that vote. So it's just a little premature at this point.
And are there any other aspects of the Iceberg project or specification or the underlying issues that it's addressing that we didn't discuss yet, which you think we should cover before we close out the show?
Oh, so what gets me really excited about the project right now is all of the ways that we didn't see initially that it's changing the way we view what our platform can do. So I could, just briefly mention some of the things that we're excited about for future work. So one of them is, we wanted to fix like being able to trust writes to our tables. And it turns out, once you can trust writing to your tables, you can write a whole lot more often, right? So if you trust writing to your table, then you'll build things that actually do write more often. So we're building a process to automatically tune our tables, do that background compaction that we were talking about earlier. Not only that, we're building something to go take a look at a table and take an individual data file, rewrite it 10 times with different settings, and figure out what the optimal settings or tuning for Parquet is for this table, and then update the table configuration so that that table is always writing optimal files. Those sorts of things we just didn't anticipate at first, but having this central library where we can configure file tuning settings at a table level, having the ability to have a background process decide, hey, I'm going to go rewrite files in this table for efficiency. Those are really exciting things. Another area where we didn't really think of this ahead of time is cost-based optimization. So right now it's a challenge to get good metrics for cost-based optimization in Spark and Presto and some of the databases that are coming out with new cost-based optimizers. Hive tables, because the data underlying the table can change at any time, your metrics may just be out of date. So when you're tracking at the per file level, you can have really accurate stats on how many rows you wrote into that file, what were the min max values in that file, and things like that. So we're getting really high quality metrics for cost-based optimization. So I'm really excited to see where that goes, because I think cost-based optimization is the next big thing for both Presto and Spark, and really going to be a huge positive win for our user base.
All right. For anybody who wants to get in touch with you and keep up to date with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
You mean other than the table format?
Yeah, other than the work that we just discussed.
I think the biggest challenge is the lack of cost-based optimization, like we were just talking about a minute ago. A lot of our users are coming from databases that can reorder joins and do some fairly simple things based on that. And if you assume that the database is going to know how to prune your partitions, the database is going to reorder joins and things like that, it's just a completely different mindset. And when you run a query, it's just slow and it seems awful. So I think that being able to really fix the plans automatically is going to widen the base of users we can serve with these systems. And I think that's a general trend that we're seeing, right? Becoming easier and easier, better and better optimizations. And that's certainly what we want for our platform. Make it so that data engineers don't have to worry about something, because worrying about how to make Spark run faster is, it's an important part of their jobs today, but we want to free up their time so they can work on, other things, more important data engineering tasks. And we want to, broaden our platform so that it can be used by anyone and not just data engineers who know how to do those things.
All right. Well, thank you very much for taking the time today to discuss the work that you're doing with Iceberg and building a reliable platform for your data needs at Netflix. So it's definitely a very interesting project and one that seems like it's bearing a lot of fruit. So I'm excited to see how it progresses into the future. So thank you for that, and I hope you enjoy the rest of your evening.
Thanks, you too. It was wonderful to talk to you. Thanks for the opportunity.